are team 42. This is our DSD project. Our idea was that many people use the same hand sanitizer or soap. So it's being touched a lot of times, and during this pandemic, this is not healthy. So our project is basically that consists of an ultrasonic sensor, is a smart sanitizer or soap bottle. This is an ultrasonic sensor where if you put your hand in front of it, wait a minute, I will make it work. If you put your hand in front of the ultrasonic sensor within a 5-inch range, it will be activated, this servo motor, and supposedly this servo motor should be connected to this bottle, but we couldn't. We should have connected this to the soap bottle or the sanitizer bottle, but we couldn't figure it out mechanically because it's a network. It's a DSD project, not a mechanics project. So we didn't care about this. We cared about the electronics part. Also this is smart bottle, so it is supposed to be placed on this FSR sensor, and if this sensor is being pressed, this LED will be 0, will be not displayed, and if it's not, it will turn red. So if the liquid inside the bottle is running low, the LED will turn red. So that's the idea of the smart sanitizer.
The FSR sensor, we used the FSR sensor to detect the pressure of the sanitizer or the hand soap. This sensor consists of two planes, which measures the difference in voltage and sends it as an analog signal. So we faced a problem since the FPGA only reads digital signals. So we had to use the Arduino to transform, which takes as an input the analog signal of the produced from the FSR and produces a digital signal to the FPGA, which sends a high value if it detects low pressure. This means that the bottle is running low, so it lights the LED here, LED 9. Yeah, now it's reading low pressure, so the LED is on. And if I apply force here, this means that the bottle is still full. So the LED is off, and if I remove my hand, it lights again because it detects low pressure.
So to calculate the distance, we used an ultrasonic sensor, this one over here. This has 4 inputs connected through this wire from the FPGA. We have the VCC, the ground, the clock, and the echo signal. The clock comes from as an input from the FPGA, and the VCC and the ground, you all know them. For the echo signal, it's a value of 1 or 0. The echo signal is the one that determines the distance. Every 147 clocks, there is a counter that we created that starts from 0 and increments by 1 every time the echo value is 1. And at the end of the 147 clocks, the counter is the distance in inches. So it looks like this.
So to explain how we calculated the distance using the echo signal from the ultrasonic sensor, like my colleague Ahmed said, we created a process that runs with every rising edge of the clock. And it basically has 2 conditions. And first, it stores the value of the echo, because we will need in the future runs to compare the previous value of echo with the current value of echo. So then it has 2 conditions. If the echo value is 1 for 147 microseconds consecutively, we will increment the counter variable we created by 1. And else, if the echo value is 0 and the previous value is 1, like we have mentioned that we will need to store the previous echo value, then this condition states that we has to change the value of the distance to a new value of the distance. So that's how we have calculated it.
And now for the motor part, the motor has 3 inputs. The first input is the ground, the second is the voltage, which is the VCC, and the third is a component that we created using VHDL that simulates PWM. The PWM takes 2 inputs, the clock and the duty cycle, and has an output of 0 or 1, which determines the shape of the PWM signal. The duty cycle of the PWM is the percentage of the duty cycle is the percentage of time of each period where the value is 1, which means that this is the time when the motor is working, as if we have 1 second and the duty cycle is 30%, then the motor works for 0.3 seconds. Period time is determined by the frequency of the clock. If the period time is less than 1.5 seconds, then
Milliseconds.
it will turn milliseconds. Then it will turn anti-clockwise, else it will turn clockwise.
The direction of the motion depends on the frequency of the PWM. So we have here in the FPGA, the frequency is already generated for the FPGA, which is constant, which is 50 megahertz, which makes the motors rotates in the clockwise direction. So we had to create a new signal that makes the motor rotates the other direction to get back to the original position. So we had to create a new signal. We had to create two PWMs. Each one of them has a different clock. We had to make a new clock which generates a slower frequency to make it rotate on the other direction. So we created a frequency of 64 kilohertz, which makes the motor rotates on the other direction depending on the distance which gets from the ultrasonic sensor.